Okay, so this unit is 4.1 and 4.2. Chapter 4 is on exponents and logs. So first we're going to start by reviewing how do we find the equation of a linear function passing through 2 points. So remember, when we do this, we start always with the slope. And the slope here would be 8 minus 2 over 7 minus 2. And that would be 6 over 5. Then from there we go into point slope. So y minus 2 equals 6/5 x minus 2. And now to get this into y equals mx plus b, which is probably what they want, even though they don't specify, we'll distribute this. So 6/5 x minus 12/5. And then we need to add the 2. So I'm just going to do that in the calculator because they want decimals anyway. So 12, it would help if I turned the calculator on, I'm just saying. 12/5, negative 12/5, plus 2. So negative 0.04. And then 6/5 is 1.2, I think. So 1.2 x minus 0.4. So that's my linear equation. Okay. For the exponential equation, our basic equation here is y equals a times b to the x, where a is my number in front and b is my base. There are a few different ways to do these, but in my opinion, using the calculator is going to be the easiest way. So if you grab your calculators, and we go to stat, and I know you're like, this isn't statistics, but follow me, and then edit, and let's clear these. We're just going to put in our 2 points. Our 2 points are 2, 2, and 7, 8. So 2 and 7, 2 and 8. Right? 2, 2, and 7, 8. Now, if we go stat and then calc, if we did the linear regression through those 2 points, see how it came up with exactly what I did? 1.2x minus 0.4. So if we go to stat and calc, where is it? Exponential regression. There it is. You got to scroll down one to find it. So then my exponential regression here would be 1.14, they want 4 decimal places? Yeah. 1.1487 times 1.3195 to the x. So the calculator will find equations of functions for you if you do stat plots, even though it's not statistics. So hypothetically, if you were taking a test and you forgot how to find the equation of a line, like if you forgot how to do this, you could just put these 2 points in and do a linear regression, and it'll find the equation between the 2 lines, between the 2 points for you. I didn't show you that earlier because I wanted you to do it by hand because I'm mean. But now that we've gotten to this point in the semester, I feel like you should know. So 1.487 times 395 to the x. That's always an option. Okay. So the calculator is always an option if you're given 2 points and you want to find the equation between them. If you're asked for a linear function, do a linear regression. If you're asked for an exponential function, do an exponential regression. Okay. So, and again, there is a way to do this by hand. I can show you if you really want me to, but it's kind of long. And it becomes a system of equations. I don't hear anybody begging, so I'm not going to do it. So we'll do the same thing for this. Was that one a y equals x? And they didn't even give us, so yeah, I'm assuming y and x. Okay. So I'm going to do the same thing for this one. Nope. Stat, edit. My 2 x's are a 0 and a 3. My 2 y's are a 5 and a 135. And then we go stat. Let's move this up a little. And then calc. And like I said, exponential regression is just off the screen. So 5 times 3 to the x. I bet you they don't even want y equals. They probably just want 5 times 3 to the x. Since they didn't give us a function, they probably just want that. Okay. So if you're asked whether a function is linear, exponential, or neither, obviously we can examine these. It's pretty easy to tell when something is linear. Like the linear one on this list is screaming at me because you see how here everything goes down by 20, down by 20, down by 20, down by 20. So this one is definitely the linear one. H of x is definitely linear. So the question is, neither one of the other two are linear. We don't have a constant rate of change, right? This goes down by 16 and then down by not 16 and then not 16. This one goes down by 36 and then not 36 and then not 36, right? So we know that a function is linear when we have that constant rate of change. Now, I'm going to use the calculator again for these because I think that's the most effective way to do them. And it's 8 o'clock in the morning and my brain doesn't want to do math. So we're going to put this in 1, 2, 3, 4, 60, 24, negative 8.8, negative 39.04. Then we'll go back to stat. Just double checking my table. Go back to stat and then to calc. I'm confident this one's not a linear regression, but I want to show you what it looks like when you put something in that's not a linear regression. Okay? Because the calculator is still going to find an equation for you. But see how your R values are not 1? Then it's not linear. If I put this in, I would get an R value of 1. So let's go back to stat and back to calc, and let's check the exponential regression and see what it says. Uh-oh. Since I got a domain error, I'm going to assume this one cannot be exponential. So we'll say neither. As a side note, the range of exponentials is only positives. So those negatives are the reason why we got that domain error. So stat, edit, still 1, 2, 3, 4, but now this time I have 80, 64, 51.2, 40.96. Stat, calc, exponential regression. There we go. So you see how here it gave me an R value of -1, R squared value of 1. That means this is for sure exponential. Okay. Now, this one says specifically, is it linear, is it exponential, or is it neither? If they asked you which one was best, you would pick the one with the best R value, closest to 1 or closest to -1. But here they were looking for, is it exponential? And if it does not have an R value of 1, then it is not like a perfectly exponential. Okay? All right, so I'll do this one both ways for you just because. So here we know that when we have y equals a times b to the x, a is my multiplier, b is my base. So here's what I want you to keep in mind. If you put a 0 in for x, then it doesn't matter what b is because anything to the 0 is 1, right? Well, b to the 0 now is 1. So when you put 0 in for x, whatever value you get there, that's going to be your a value. So why do I tell you that? Because that's where it crosses the y-axis. So if this crosses the y-axis at 3, then that means that my a value is going to be 3. So now I have y equals 3 times b to the x. Find any other point. We could use this one right here, 1, 6. And plug in. When x is 1, y is 6. Well, b to the 1 is just b. And if we divide both sides by 3, we'll get that b is 2. So then my equation is y equals 3 times 2 to the x. Now, you could have absolutely took these 2 points and put them in your calculator the same way that we did for the other ones. And you would have gotten this. Okay, so that's always an option. All right. So describe the long run behavior, that's end behavior, of, let's graph it. I'm going to graph it and then we're going to talk about, when we're looking at the graph, we'll talk about what all these things did to it. -5 times 2 to the x plus 3 plus 2. So we've talked about translations before. This plus 3 shifts it left 3. This plus 2 moved it up 2. But really, those aren't going to have a huge effect. They are on one side, actually, of the end behavior. This -5 reflected it over the x-axis. So our normal shape for these looks like this. That's the basic shape of an exponential function. Just like you know that the basic shape of a parabola is the basic shape of a quadratic is a parabola, the basic shape of a linear function is a line. This curve is the basic shape of an exponential. So on this side, it goes up forever onto infinity. And on this side, it meets an asymptote at y equals 0. That means that it's approaching the x-axis, but it will never cross the x-axis. So looking at this, I took this, I shifted it left 3 up 2 and reflected it over the x-axis. And that's how I wound up here. So on this side, on the right side, you can see that as we go, as t goes toward, ooh, look at that. I did it in the right order this time. On the right side, as t goes toward positive infinity, f of negative t is going toward negative infinity. Right? See it? Now on this side, on the left side, it's definitely asymptotic, so it's getting close. We have to figure out to what number. So this is going to be my key number here, because normally this is at 0. but we shifted it up 2. So that moves that asymptote on the left side to 2. So this 2 is the reason why this is 2. If this had been an 8, this would have been an 8. Okay? The only other thing I want to mention is that this is when b is greater than 1. If your b value is a fraction, then this is your basic shape. So then your end behavior flips around. Next section. Any questions on that section?